So our next speaker is Abdellah Tounsi from Constantine Quantum Technologies and the University of Constantine one in Algeria. And in his talk, he will tell us about systematic Braid matrix generation for topological quantum computing. Please, Abdellah, the floor is yours.
Thank you, Taha. Hello, everybody. In this talk, I will discuss the Braid matrix generation in systematic way for topological quantum computing. The Braid matrix are the elementary quantum gates in topological quantum computing, so it's important to be able to compute them in systematic way and easy to be implemented in numerical networks. So in this talk, we are going to introduce some basic concepts of topological quantum computing and basically anyons. Then we are going to define anyon models, which are the main framework for the theory behind topological quantum computing. Third, we are going to go through some techniques to compute such Braid matrices. Finally, I will share with you some results using this method. So we know that quantum computing is so promising to solve many problems. However, we know that quantum systems are noisy and struggle requirements. So it is necessary to make fault-tolerant quantum computation. For that, we have two big frameworks. The first one is a software solution that includes quantum error correction codes. But of course, it needs low error rates and high fidelity quantum gates, typically error rate of 1 in 1,000. And moreover, to encode a logical qubit, we need a large number of physical qubits. On the other hand, topological quantum computing is a hardware solution, and it needs even lower error rates and good control of systems. The benefit of topological quantum computing is to encode logical qubits in less number of physical qubits. So what is topological quantum computing? The main idea behind it is to encode quantum information in non-local parameters, or generally, they are topological parameters. The benefit of that is to protect the information from local noise. As we see in this picture, we have a Mobius strip, and it is obvious that you cannot distinguish locally between this strip and cylinder. So we should always make a loop around this strip to differentiate between the two. So topology can give rise to such non-local parameters. In physics, we know that topology can emerge in the anyonic systems. Anyons are quasi-particles which have exotic statistics. What do we mean by statistics? In physics, statistics is the mechanics of exchanging or swapping two identical particles of same or different states. So as we see here, and in 1977, Linus and Mirhai proved that such exchanging process can produce a statistical phase factor, which is the phase phi here. So this can be happen in two-dimensional space. So anyons live in two-dimensional space. So what is the idea here is that we can implement quantum operation and make change in the state just by exchanging particles. So in summary, the quantum state of anyons is determined by their space configuration or their arrangement, and the quantum evolution of such systems is described by braids. So exchanging two particles in two dimensions is equivalent to braids in space-time space. So as we see in the figure, the braids since we are interested in statistics, we don't mind by geometry, by just topology. So topology of grids is immune to local disturbances. This idea make Derive to propose such systems to make or process quantum information. Mathematically, grids are described form a grid group. In the Braid group, we have Braid generators, which are sigma i's. Sigma I is the process of exchanging or breeding two adjacent anyons in our configuration. For each Braid generator, we have the inverse Braid generator, which is its mirror image. And in this Braid group, we have as a characteristic algebra, which is the Young-Baxter equation, as you see in the right side. So these two Braid patterns are topologically equivalent, and algebraically it gives a restriction on the segments. So by concatenating this Braid generator, we can create any breeding sequence. So statistics of anyons is not enough to encode quantum information. To be able to encode quantum information on anyonic systems, we have to introduce the fusion processes or fusion rules. So here we define an anyon model which includes a set of anyon charts, 0, which is the vacuum, and other charts, C1, C2, etc. And fusion rules. In fusion rules, we define the allowed process fusion processes. For example, here we can fuse A and B to I and G and etc. Depending on fusion rules. Here, for example, we have the Fibonacci anyon model, which is a very simple anyon model that contains two anyon charts, the vacuum and Fibonacci anyon, which labeled 1 as well. The non-trivial fusion rules here, they are so simple. We have two anyons that can fuse to 0 or can fuse to another Fibonacci anyon. Surprisingly, this simple anyon model, which is based on defining simple fusion rules, can construct a universal quantum computer, and this is proven by Friedman and others, and it's very important for these systems. Let's consider 3 Fibonacci anyons with same fusion rules. So we have 3 possible fusion states, and we can separate this space of states into 2 sectors. A sector where the anyons globally fuse to 1, and the sector of 0. So in the sector of 1, we have 2 possible fusion states, and we can encode qubit. In the other sector, we cannot encode non-trivial quantum information. But if we sum them together, we have a qubit. And when we consider more than 3 Fibonacci anyons, the Hilbert space or fusion space of this system grows exponentially. There are many anyons or anyon models in theory, but in experiment, very recently we have the creation of non-abelian anyons, specifically Eisen anyons by Google Quantum AI. You see here they managed to read Eisen models in experiment, lattice of qubits since conduction processing. Another experiment from Continuum, where we see here Braid patterns of another anyon model, the quantum double V4, and this is implemented in their latest quantum H2 ion quantum computer. So our main question is how to compute such matrix representation of such Braid operators on specific on general fusion states. So in general, we should know the action of each Braid generator on each possible fusion state. So this constructs components of these matrices. Luckily, it is proven that fusion and rotation matrices are sufficient to do such tasks. So what are such things? First, fusion matrices are transformations, basis transformations from between different fusion orbits, given three anyons, like we see in this diagram. So the F matrix components should be probability amplitudes and should preserve the normalization of states. On the other hand, we have the rotation matrices R, as we have seen in the beginning, exchanging two anyons A and B should give rise to statistical phase factor. And since we have different or multiple fusion outcomes, so the pure statistical phase factor should be the R matrix should include all the possible statistical phase factors depending on fusion outcome. Here, fusion outcome is I. So the components of R are RAB I. How we use fusion and R matrices in practice? We have, let's consider this case where we have three anyons, and we want to make a braid in between the second and third anyon. So we should first apply the F transformation. Then after that, we are able to apply R transformation. Then we go back to the initial fusion order by using the inverse fusion matrix. The product of such transformations R and the inverse of F constructs what we call the breeding matrix. This breeding matrix is beneficial because we can apply it on more general cases like what we see here in the bottom. So the topology allows us to implement the breeding matrix in this case because they have the same topology. So on the other hand, we need also a mixing matrix for this more general case. So here we cannot use the breeding matrix directly, so we should use also a series of F transformations to get the fusion tree in the right side. So here in this situation, we can apply the breeding matrix and go back again to the initial fusion order. So product of all such transformations will construct or give us the mixing matrix. And this gradient matrix and mixing matrix give us a simple way to make numerical computation of such gradient generators. So this is our draft that will be published with arXiv as soon as possible. And it will include all of the technical details of these processes. So as a result, let's get a concrete example of the 2 qubits with Fibonacci anyons. So we have here 6 Fibonacci anyons. We want to represent 2 qubits with 3 anyons per qubit. So the fusion space dimension is 13, so you have 13 possible fusion states. So Braid generator should be 13 by 13, and we can notice here that these Braid generators are reducible to 2 sectors, sector 0 and sector 1, as we have seen before. So this matrix should verify unitarity and the Braid group algebra. This is a strong condition to verify such matrices linearly. Again, might make more verification. So we have reproduced the synod gates using the Braid matrices. The synod gate can be approximated using injection method as being designed by Boston and others before. So we have here the 13 by 13 Braid matrix, and we can notice the signature of synod gate in sector 0 and in sector 1. And the importance of such numerical computation is to compute the accuracy and leakage and many properties of such Braid sequences. All such implementations are now possible and valuable to do with our TQSIM open source package. This TQSIM will be presented by Nasser in the next talk. So thank you for your attention.
Thank you very much, Abdellah. Thank you for the next talk, and it's great to see that quantum simulation performed by Google and Quantinuum is once again in the spotlight to explore new insights in such exciting approach like topological computing. So let me take some questions. So one question in the chat is there Braid generator software or SDK? So I guess the answer to this is rather straightforward.
Yes, actually, we did this study to construct using an open source package to simulate such Braid sequences on ultimately on different anyon models.
Yeah, and this will be the subject of the next talk. But before moving to that, I just want to ask you a question, Abdellah, to make things clear for our audience. So, in your opinion, what's any specific advantage of topological quantum computing compared to other quantum computing approaches?
So the first thing is to make quantum computation robust to local noise and decoherence. So this is the first motivation of topological quantum computing. As I said in the beginning, there is two approaches: quantum error correction and topological quantum computing. The advantage of topological quantum computing is to encode logical qubits in less in small using small number of physical qubits. I mean, this is very important for scalability of quantum error correction.
Great. So another question, the reason why the Braid matrix is so important is that we can obtain the classic quantum gates we have by using it.
Actually, I don't have.
So I think a reformation of that question should be: is it possible to retrieve any kind of classical gates or conventional gates, conventional quantum gates using this Braidian approach?
Yes, this is another topic in quantum computing. Actually, what we are interested in is to make quantum computation universal in topological quantum computing. So if it is universal, we can do anything we can do in conventional quantum computing. So if classical gates are possible to simulate with quantum gates, so it's also possible with topological quantum computing. So there is a map one-to-one between the grid gates and the conventional quantum gates. So there is no difference. We can do everything that we can do in conventional quantum computation. So we just change the system, but it is the same computational framework.